A matrix is orthogonal if we can say that P transpose P is equal to I. As a consequence, it means that P is equal to P transpose is equal to P squared. They're all the same. So if this is true, it means that P is orthogonal. Now, if you remember in chapter 4 when we were talking about pseudo-inverse, we said that if G is pseudo-inverse of A, in order to prove it, there are 4 properties. We have to check all the 4 properties. The first property was if G is P inverse of A, we have 4 properties. And the property 1 was AGA is equal to A. Property 2 was GAG is equal to G. Property 3 was AG transpose is equal to AG. And property 4 was GA transpose is equal to GA. So, what is the hypothesis here? It says that P plus is equal to P. Right? In other words, the pseudo-inverse of P is itself. Let's see. So here, can you tell me that what is G? Is P. What is A? It is P. Right? So let's see. Property number 1. P multiplied by P multiplied by P is equal to, what is this one? P squared P. But what is P squared? It's P. So it's P multiplied by P, so it's P squared again, which is P. So first one, satisfied. Second one, the same as above. Why? Because it's P multiplied by P multiplied by P. The third one, P multiplied by P transpose is equal to P squared transpose is equal to P transpose. But what is P transpose? Because it's orthogonal, it is P. So this is also true. The first one is same as above. Let's do one more question. And it is one part of question number 3 of chapter 7. This was question number 1 of chapter 7. This is one part of question number 3 of our chapter. And it says, prove that I minus A plus A is an orthogonal projection. Now, the question is, how can I prove it? How can I prove that something is orthogonal? We look at the definition. We square it and we see if it is the same term that we have. If it is, done. Or you check this one, or you check this one, or you check this part, or you check this part. So any of this one will result to the same thing. So go ahead, try to see it. See what is I minus A plus A squared. So we do the multiplication, it's I minus A plus A minus A plus A plus A plus A plus A. What is this? So this is A plus. Look, I cannot say this is I. I cannot say this is I. But I know that this and this is always true. Right? So this term is A plus. So what I have is I minus A plus A minus A plus A plus A plus A. These two are cancelling each other, so I'm getting I minus the pseudo inverse of A multiplied by A. So it means that it is orthogonal projection. All right. Any question? So let's start the new topic, linear list S-squared problem. And this is pretty important in many aspects of science, also in computer science. Now, what this problem tries to do in general is this. We have sets of data, right? And we try to find a line, which pass through our data. And if we are calculating the error, it has the minimum value of this error. Now, we understand that there are several ways of calculating this error. One is that you can have lines which are, let's say, we call them vertical lines. So, and we call them delta. Delta is the error. So I can add all the delta squares, and I want to get the minimum number. Usually in chemistry or in physics, previously we have seen that we have delta defined to be perpendicular to this line, right? This is also one way of calculating the error. And if you are finding this error line, which is perpendicular to our fitted line, we call it the total least square. But in general, if you minimize it for the black one, it will also minimize for the other one. And some people are using horizontal lines and try to minimize that one. Okay, so the problem is this. We want to find that line. The problem is we want to find the singular values. You want to do the singular value decomposition, you need to calculate all the matrices. The problem is we want to use this QR decomposition, and we have to find these values. The problem is we want to find the intersection, the root of a polynomial. So, and this is not a very friendly one, so you have to approximate it. So as you can see, this least square problem is everywhere. You want to calculate the pseudo-inverse, you need to use this least square problem. So this is very handy because it helps you to come up with some model which you can minimize it. Do you know what is the profit of minimizing something? If you can model something in a form that you need to maximize or minimize it, do you know
What is the power behind it? It means that you can use all the strong optimization theory behind it in order to get to the results. So it is very beneficial if you manage to model what you are doing by using this least square problem. Of course, if we talk about the linear one, but you can go ahead and have more complicated system which is non-linear. But again, the story is that you define an error function and you try to minimize this error into a 0. We always have this error function, even if you have a very simple situation. What is the simple situation? I have this data and I have this data. Do you know what is the best fit? The best fit is that I have 2 points, definitely I can draw a line. And now can you tell me that what is the error? Here the delta is 0. I mean the E delta as a function is 0. So we have the error function also here. And it has its own minimum value, which is 0. Okay? So this problem, although we don't see it, it always exists. And we will see that why usually we have it, because in some terms we have some arbitrary part and we cannot get rid of that arbitrary part. Okay, so let's define the whole thing in the mathematical form, which says, suppose we have a matrix of Rn by n with m is greater than n and B belongs to Rn, then the linear least square problem is defined or is consists of finding an element of the set, in my blue pen is dying, of the set of this form. This is a vector space X, and it is those vectors of X belonging to Rn, where rho is the error, rho of X, which is the norm of Ax minus B2 is minimized. I use norm 2. You can use norm 1 and minimize norm 1. You can use norm infinity and minimize norm infinity. You can use F norm and minimize it. But they are very difficult to calculate. This one, norm 2, is much easier to calculate. That's why we are using norm 2 in our calculations. But keep that one in your mind. If you hate norm 1, norm 2, and you want to use, let's say, other type of norms, feel free to do it. But it doesn't change the aspects. So, let's continue, and then I will tell you some other visual representation. A vector X belongs to vector space X if and only if A transpose R is equal to 0, where R is equal to P minus AX is this important term, is the residual associated to X. Residual means the error. If R was 0, then we were in a very good situation. Now, let's look at the definition once more, try to understand what it does. And this is actually something that when I was talking about the pseudo-inverse, if you remember, I actually gave this example. It says that A belongs to Rn by n. Okay? So, let's see what it means. A 1, A M1, A1N, AMN. On purpose, I make it in this form so you understand that M is greater than N. M is greater than N. How many X values will we have? N. Otherwise, we cannot do the multiplication. How many values of P will we have? Now, look at here. Look at here. Let me give you another hint. Let me write it in a more systematic form which you might remember, because you know that this is sets of equation. A11, x1, A1n, xn is equal to p1. And it goes A m1 x1 plus A mn xn is equal to bn. Can you tell me that what can we say, what can we observe from this? What is our observation from what I have written in here, or what I have written in the same thing in the matrix form in here, or as a set of equation? What is the observation? Number of equation is bigger than the number of unknowns that we have. I have 3 unknowns, but I have 5 equations, right? Now, if I have 3 equations and 3 unknowns, and assume that they are not parallel to each other, do you know what is the solution? If the solution exists, what is the solution? If I have a unique solution, 3 equations, 3 unknowns, and I have 1 unique solution, what does it mean? It means that there are 3 lines which are intersecting at one point. Look. Three equation and 3 unknown, okay, and 1 unique solution. If it exists, it means that in the Cartesian form in 2D, I have 3 lines, and these 3 lines, all are meeting at one point. All are meeting at one point. But imagine that I have 3 equations and 2 unknowns, and these 3 equations are not linearly depending on each other. In other words, I cannot ignore one to say 2 equations, 2 unknowns. Then it means that I have the blank scenario, which is, you should remember this example. We had it before. Do you remember? Then 3 equations, 2 unknowns. How many solutions do I have? It seems I should get 1 solution, but it has 3 different intersections. In other words, there is no point which all of them are intersecting with each other. This was the situation that we said we need to define A plus, because A inverse does not exist, right? A inverse does not exist. Why it does not exist? Because M is greater than N. And even if M was equal to N, it means that it was a singular situation if we have something like that. Then if you remember, I was doing a numerical example for all of you, and then I said that if I use the pseudo-inverse, and I calculate what it does, it tells me that the intersection point is this point. Do you remember what was the property of this point?
It always exists.
Sorry?
It always defined.
Yes, but it has a very important property, and I told you that we will come back to this example later.
It was calculated with the least square.
Exactly. if we calculate the least square, we will see that this has the minimum distance from the whole point. And actually, I said in MATLAB, it calculates a plus the pseudo-inverse by using this least square problem. Okay? So this is how, you know, chapter 4, chapter 5, and now chapter 8 are related to each other. We are talking about the least square problem. This is how we are noting it. This means what we saw before at the end means that what we had in chapter 4 when we were talking about the pseudo-inverse. So if such a case happens, we have a matrix called R, which is the residual of our vector. Residual means that for this part, I have one residual vector because I'm supposed to be the blue one, but I'm in the green one. In here I have another one, in here I have another one. If R was equal to 0, it means we are here. We have this situation, right? So the problem is that R is not 0, and we try to minimize this R. Now, believe me that a vector x belonging to this vector space x, you may remember we had the proof in previous chapters, if and only if x is of the form plus I minus a plus a y, where y belonging to Rn is arbitrary. So it means that in such a situation, I can find a solution, and my solution consists of two parts. A unique part, so always I have the unique part, plus then arbitrary part. In the example that I just erased with the red lines, you know, 3 lines which were intersecting at the same point. Can you tell me that for that scenario, what will be our conclusion regarding to this x? I have 3 equations, right? And 3 unknowns, and they are all passing through one point. What does it mean?
There will be no arbitrary part.
It's excellent. It means that I have unique solution, which means that there is no arbitrary part. Okay, no arbitrary part, but I want to take y to be less than 1. 1, 1, isn't it? So what is the condition to guarantee that I don't have an arbitrary part?
More equation.
No. Look at here. Suman, tell me what is the condition that guarantees me that the arbitrary part is 0?
That part is 0.
Sorry?
Why is that?
A plus A should be high.
We have unique solution if a plus a is equal to I. Then no matter what is y, if this is I, the result is multiplied by 0, and I am left to be arbitrary with the unique part. Okay? Also, we understand that this is a definition. This star, they are all the same, just different way of noting it. And we have another notation of the same thing, and it's called the vector space X is called convex. So let's see what it means. X is convex. In other words, if x1 and x2 belong to our vector space X, and theta belongs to 0 to 1, then theta x1 plus 1 minus theta x2 also belongs to X. Okay? Now, we can also, from this notation, we can also get one other observation. That vector space X has a unique element. We call it X star of minimal second order. Can you tell me that? What is that X star? It says that the X, the vector space X, has a unique element called X star, which is the minimal of the second norm. Can you guess what should be the X star? I mean, the answers are actually on the board. You have to just do a very simple matching. What is X star? Unique. What is unique? A plus B. In fact, X star is A plus B, which can be obtained by solving. Now, why we say minimal second norm? I was expecting to see this question from you, that where is the second norm that we want to minimize it, and the second norm is this. You know that X is in this form. I can write it as second norm of X squared is equal to let me write it as X star, which we know that is A plus B plus I minus A plus A y. Now, can you tell me why, if it is minimum, if I minimize this second norm, I get the unique part? In other words, if X plus is solution of minimizing this second norm, it is unique. Can you show me that if X plus is achieved by minimizing the second norm, then it will be the unique part? Now, can you tell me when do I have the minimum value for X norm squared? When? Look, this is non-negative, right? And this is something that I try to find. This is, it should be minimized. This is also non-negative. So what is the minimum number of this one? 0. So mean is when it is 0. Because if it is not 0, I am adding. So if it is 0, I get the minimum value. I want to have the minimum of this second order, right? So this is minimum if this is 0. And we understand that if this is 0, it means that x is, which is our x star, is a plus b. I mean, it's not very, very complicated. It's just kind of like playing with words. One equation, and we are just driving all other things. You have to be careful about all of the single words that we are using, right? So the unit solution happens when we have a plus a is equal to a to I. Can you tell me that? I think I have written this at least 4 or 5 times in the class. You have seen it from chapter 1 even. Can you tell me what does it mean? A plus A is equal to I. Let's put the question in this form. Maybe it will be much more friendly to you. When do I have in this system of equation, Nastia, when do I have a unique solution? Actually, all of them are independent. The equation?
No, the equation before the
Left part, right part. Put the sentence in correct form. When do I, for this one, when do I have unique solution? In other words, all my lines are passing through one point. When number of equation is equal to number of unknowns. Then n is equal to n, and all of them are linearly independent. All of these sentences is one expression. Do you remember it? Excellent. This means rank A is equal to n. I don't mind if I have n equation. If rank is equal to n, it means that n of them are independent, the rest are linearly dependent. So I can just throw them away. So this means that the rank A is equal to n. Now, here, as you see, Ax is equal to B. B is a vector. You can have B to be also a matrix. In other words, let A, so we are making it from vector into a matrix, belongs to R m by n, and B belongs to R m by k. Then the general solution to minimizing of x belongs to R n by k of A x minus b, the second one of this one, is of the form of, can you guess what should be the general form if we have everything as a matrix? Before we had it as a vector, so we had an x which was a vector. Now x is a matrix. A plus b plus I minus A plus A, the matrix Y, where Y is arbitrary matrix. Can you tell me that what should the size of I? Y. N by K, exactly the same as Rx. What is this? The unit part. This is the unit part, and this is the. And if we have a solution, a unique solution, it means that our arbitrary part is equal to 0. I stop here. I mean, although we do not cover all the subsections of this section, in other words, very small length from this section. However, in order to produce further, I want you, please, by Tuesday when we have our class, revise the previous sections. Because I understand, I can see in your faces, many of you do not remember, not you don't know it. You do know it, because as soon as I tell you that it was rank N, I can see the blinks in your eyes. But read them, otherwise you cannot make the leap. You know, the examples we had in chapter 4, we are in chapter 7, we get back to them to say that, look, this is the same problem, but we are looking from this point of view. One of the aim of this course was and is that you will start to have a very analytical point of view to your own research. One problem, we use pseudo-inverse, we use singular variety composition, and now we are talking about the least squared problem. So we can solve one problem with different methodology. Which one do we have to choose? You have to look at your computational complexity. You have to see which one give more accurate results. We understand that the other two, the first two that I mentioned, are actually being calculated by this least squared problem. So please review them. Like maybe on Monday, you review them so you have them back of your head. Then you can have more interactive session that I'm telling you that, look, this gives you that and this gives you something else. I will also try to give no more homework. I will give one more homework, so we will stop by 8 homework. I bombard you a lot with the homework. But I will solve some sample questions in the class. All right? We have one more chapter which is very important, and we definitely want to talk about it, and it's ion vectors, ion values, and ion vectors. So it means that we have quite plenty of time to while we are talking, because that chapter is also like this one. We have to go back and suddenly we talk about chapter 3 and to the chapter 5 because we want to conclude something in the new chapter. So we can spend more time on that important aspect. Do you have any question? If not, this is the end of the lecture for today.